Okay, this is lesson 3 of module 5. We're going to be talking about linear functions in this lesson. In the last lesson, we talked about what the definition of a function was, and now we're going to look specifically at linear functions. Okay, so this example that you have in your classwork, example 1, is a table that we looked at in the last lesson. It's a table of inputs and outputs, and we can see that it fits the definition of a function because there's exactly one output for every input, or every input has its own output. And we could say that cost is a function of the number of bags of candy that are bought. So we're going to use that type of language as we define functions. So, but what would a linear function be? So you might be guessing that a linear function would graph as a line, it would have a constant slope, and we could find a linear equation that would describe it. In other words, its rule would be a linear equation. So as we look at the values in this table of values, you might be noticing some things numerically. So if I spend $10, I can get 8 bags of candy. So that would be $1.25 per bag for buying 8 bags of candy. And if I check some other values here, $7.50, I can get 6 bags of candy. So that would be $1.25 per bag there. So we can see this is a proportional relationship. The ratio of y to x is the same for all the values in the data table. And I can see that at the 1 bag of candy entry right here, 1 bag of candy is $1.25. So this clearly represents not only a linear relationship, but a proportional relationship. Okay, so I can see that the rate of change is the same for each of these points, or the slope value. And if I plot the points, I can see they're forming a line. And I can write a relationship for this. So I can write that since it's $1.25 per bag of candy, that's the rate, I can say y is equal to 1.25 times x. So if x is 2, that means 2 bags of candy. I'm going to multiply $1.25 times 2. So that is a proportional relationship because it goes through the origin. And so the 0.00 would be part of it. If x is 0, y is 0. Okay, and another thing we talk about with functions is constraints on the variables. So in this particular example, the inputs, the x values, have to be non-negative integers. So they have to be 1, 2, 3, because they're bags of candy. You can't buy 1.5 bags or 2.5 or -1 bags. So x is a non-negative integer, and y is going to be positive as well. So those would be the constraints on the variables there. Okay, let's look at example 2. This would be a constant rate problem, a distance time problem. So Walter walks at a constant speed of 8 miles every 2 hours. Describe a linear function for the number of miles he walks in x hours. What is a reasonable range of x values for this function? Okay, so we would need to start by first finding his rate. So he goes, some number of miles in x hours, and that's the function we're trying to define. So we have some data. We know that he can go 8 miles in 2 hours, and that's his constant rate. So I can set that equal to y, and y is going to be our distance traveled over x, which would be time in hours. So by then cross multiplying here, I can see that, I'm going to have 2 times y is equal to 8 times x. And after I do that, I can put it into this functional relationship right here. This is our linear equation, y is equal to 4x. Probably could have gone directly to that, noticing that his rate is 4 miles per hour. So you might have seen just to go straight to this, y is equal to 4 times x. Okay, so the second part of this says, what is a reasonable range of x values for this function? Well, certainly x is going to have to be greater than 0. And so we could put that on there, greater than or equal to 0. There might be a reasonable number of hours that he could potentially walk, but we really don't know if this is, what the time length is. So we know that at the very least, our time has to be more than 0 because we cannot travel backwards in time. So since x is going to be positive, then our distance, the distance will also be positive. Okay, our next example is also distance and time. So this is Veronica, runs at a constant speed. The distance she runs is a function of the times she spends running. And we could have said that similar type of statement for the last example as well. The function has the table of values shown below. So if she runs for 8 minutes, she can go 1 mile. If she runs 16, it's 2 miles. So again, we're seeing here a proportional relationship. So we can look at her rate. We can see that her rate is if she goes y miles in x minutes, we have her going 1 mile in 8 minutes. And so she goes 1/8 of a mile per minute. Okay, so we can look at that. We can write the relationship 8y is equal to x times 1, dividing by 8. We see that y equals 1/8 x. Or we could have seen that that rate was 1/8 and gone directly to the y equals 1/8 x. And once again, our x and y values are going to have to be positive because we're talking about time and distance. And again, if we want to describe the function in words, we would say that the distance that Veronica runs is a function of the number of minutes that she spends running. All right, example 4. Water flows from a faucet into a bathtub at a constant rate of 7 gallons of water pouring out every 2 minutes. The bathtub is initially empty and its plug is in. Determine a rule that describes the volume of water in the tub as a function of time. If the tub can hold 50 gallons of water, how long will it take to fill the tub? All right, so if we're going to write the rule that describes the volume of water in the tub as a function of time, we need to know what the rate is. So we would need to know, and that is what we want to do, we would need to know how many gallons per minute are flowing. So gallons per minute is going to be our rate. Y in our rule is going to stand for gallons and X is going to stand for minutes. So that'll be Y over X. It's a constant rate, we're told. And so we know that we can use this 7 gallons every 2 minutes as a constant rate. So that would be 3.5 gallons per minute. This is a proportional relationship when the tub starts out with 0 water in it. So I know that the number of gallons, Y, that flows out is going to be 3.5 gallons per minute times the number of minutes. So for every minute that it's flowing, 3.5 gallons is going out. So that's our proportional relationship right there. And so now I'm asked, if the tub can hold 50 gallons of water, how long will it take to fill it? So what I want to do is make Y equal to 50 gallons. So 50 is equal to 3.5x. If I divide by 3.5, I get the time. X is the number of minutes that it takes to for the faucet to fill a 50-gallon tub. And that would be approximately 14.3 minutes. It didn't come out exactly even, but approximately 14 minutes. We could even round it off to that. All right, now we're going to assume that we're filling the same 50-gallon bathtub with water flowing at the constant rate of 3.5 gallons per minute, but there were already 8 gallons of water in the tub. So will it still take 14 minutes to fill the tub? Well, I hope not, because there's already some filled, so it should take less time. So let's look at that. And what I'd like to do is just start filling out this table and then write a rule for this equation as well, just so you can see what it would look like. So at time 0, there are already 8 gallons of water in the tub. So we can put that point into the data table. And from there I can see that I can write this relationship, because I know that I'm having 3.5 gallons per minute. So that's this part. And then the 8 gallons is going to add to the total in the tub, which is y. So y is going to equal 3.5x plus 8. If I want to know how long it's going to take to get 50 gallons, I can put in 50 for my y value, which is what we've done. And then I can begin to solve that equation. So first I would subtract 8 from both sides and get 42 is equal to 3.5x. Next I want to divide by 3.5. And I get x is equal to 12. So it's going to take 12 minutes to fill the tub, which seems reasonable. 14 minutes to do the 50 gallons. If I want to do only 42 gallons, it's going to take less, so 12 minutes. So let's fill in the rest of the data table with the values. So in 3 minutes, I would want to put 3 into this equation. So I'd get 3.5 times 3 plus 8, and that's 18.5. And that can go in the data table. For x equals 6, I get 29. For x equals 9 minutes, I'm going to get 39.5. 3.5 times 9, and then plus the 8. And then for 12 minutes, which is what we found here, if x is 12, then 3.5 times 12 is 42, plus 8 is 50. So there's our 50 gallons at 12 minutes. So I hope you're noticing the y equals mx plus b format of these linear equations that are being used as a rule for this linear function that's described in this problem. So another way to restate this function again is that the total volume of water in the tub is a function of the time that the faucet spends running. Okay, example 5 is a similar context of water flowing from a faucet at a constant rate, but this problem's slightly different. Okay, so we are told that there are 6 gallons of water already in the tub at the time that we notice the faucet is on. And then the data table gives us information for 3 minutes, 5 minutes, 9 minutes. And so what we need to do is we want to figure out a rule for this function. We know it's linear because we have a constant rate going on. So we need to find out what that rate is. So as we begin to do that, we realize that the rate is going to be how much does the volume in the tub change in a given amount of time. over time. So if you look at this first entries here, from 0 to 3 minutes, the time that passed was 3 minutes. The volume changed from 6 to 9.6. So that's like finding the slope, right? So I take 9.6 minus 6 to get the change in volume. 3 minus 0 gives me the change in time. So I get 3.6 divided by 3, which simplifies to 1.2 gallons per minute. So if I checked some of these other, the slope between any 2 points on this graph, for instance, this one, 16.8 minus 12 is 4.8, and the change was in 4 minutes. So I could also see that that would be 1.2 gallons per minute. Okay, so we're told it's constant, so that would have to be true, that the slope between any 2 of these points would be 1.2. All right, so we can now write the rule because we know the rate and we know the starting condition. So we can write our rule as the rate times the time that the water's flowing, so 1.2 times x, which is time, plus 6, because we started with 6 gallons. So if you look at this at time 0, this term would be 0, and y would equal 6. And there's our 0.06. And so what we would want to do is check our rule with some of the other points here. So if we want to check the rule for 5, we're going to put 5 in for x and evaluate this. 1.2 times 5 is 6, plus 6 is 12. And there's our input-output pair for 5 minutes. An input of 5 minutes gives me an output of 12. So this rule is working for this function. And we could check it with the 3-minute and the 9-minute as well. Okay, there are 3 exercises for you to work on independently or with somebody, a partner who's working with you. But if you want to try those first and then come back and check your results with the video, you could do that. Notice that most of what we're doing here is just adding some vocabulary to the linear equations experience that you've already had. So it shouldn't be terribly new to you. So pay attention to the vocabulary that's being used, because functions are such an important concept in mathematics that catching on to some vocabulary now will help you later. Okay, so go ahead and pause and work on those exercises. Okay, so for exercise 1, Hannah claims she mows the lawn at a constant rate. The table below shows the area of lawn she can mow over different time periods. So in 5 minutes, she can mow 36 square feet and so on. So the first question that's asked is the data presented consistent with the claim that the area mowed is a linear function of time? So she's claiming a constant rate, and so if we graph these, so there's a number of things you could have said here or done. Maybe you tried plotting them and noticed that the graph is a line, or you take her word for it. This is a constant rate. If this is a constant rate, then it's going to be a linear function. Okay, and we'll see more numerically about that in part C and following. Okay, so for part B, describe in words the function in terms of area mowed and time. So the way we'd want to say that is the area mowed is a function of the time spent mowing. So notice that when you write these statements, you're going to always have is a function of in the middle. So the area mowed, so this is going to be the dependent variable, is a function of the independent variable, time spent mowing. So that's going to be the pattern for stating these functions. Okay, so now we're going to really use the data and prove it. So we're asked, at what rate does Hannah mow lawns over these different time periods, 5 minutes, 20, 30, and 50? And so if we do the calculations there, we see that 36 feet squared in 5 minutes works out to 7.2 square feet per minute. And actually, all of these do. So her claim that she is mowing at a constant rate is true. You're asked in part G to write the equation, and since it is a constant rate and it's a proportional relationship, it's a really easy one to write. It's just her rate times the amount of time that she spends mowing. So y equals 7.2x. If she doesn't mow at all, if x is 0, then y is 0. So this is a proportional relationship. The limitations on x and y are the same because we're dealing with time. So time has to be greater than or equal to 0, but she could do fractions of a minute, obviously, so it doesn't have to be an integer. And the area that she mows, y, is also going to be greater than or equal to 0. Okay, so part I, what number does the function assign to x equals 24? That is, what area of lawn can be mowed in 24 minutes? So pay attention to this vocabulary. Functions, one of the ways we talked about it is that functions assign values to the input. So I have an input of x equals 24. The function is going to use the rule and assign an output value to it. So what number does the function assign to x equals 24? Well, all I have to do is put that into my rule, use my rule, 7.2 times 24, and I get 172.8 square feet. So that would be the output value for an input of 24. According to this work, how many minutes would it take to mow an area of 400 square feet? So now what I want to do is use my rule, and put 400 in for the amount of square feet mowed. So that would be, put that in for y. So 400 would equal 7.2 times x. So to solve for x, I would need to divide by 7.2. And I get 55.5 repeating, which is approximately 56 minutes. Okay, exercise 2, hopefully you've tried it on your own. This is a linear function, and this is the table of input-output values. For it, it's volume of water flowing out of a hose. We're asked to describe the function in terms of volume and time. So this would just be using words. So the volume that flows is a function of time. Again, volume is the dependent variable, and it's a function of the independent variable time. All right, part B, we want to write a rule. So if we're going to write a rule, we need to know what the rate is. So 44 gallons flows out in 10 minutes, so that'd be 4.4 gallons per minute. I'm going to double check that with a couple other points just to make sure this is a proportional relationship, and I find out that it is. So it's y equals 4.4x is going to be the linear equation that will be the rule that defines this function. Okay, so what number does this function assign to 250? In other words, 250 is my input. What is it going to give me for an output? So all I need to do is put that into the equation, and not forgetting there's a decimal point there. Put that into the equation, and I get my answer of 1,100 gallons. So in 250 minutes, 1,100 gallons flowed out. Okay, in part D, we're given this swimming pool and told that the pool is already 1/4 full. We want to write an equation though that describes the volume of water in the pool. If at time 0, we use the hose described above that had the rate of 4.4 gallons per minute to start filling the pool. Okay, so it'll be useful to know how much water's in the pool. So to find that, I'm going to take 1,000 or 17,300 and divide it by 4, and that gives me the number of gallons that are already in the pool. And now I want to write a rule. So I know the rate, and again, these are y equals mx plus b rules. Any linear equation can be written that way. So I've got y equals 4.4x, and if the pool had no water in it, this would be the equation. But it does have water in it. It has that much water in it. So the equation becomes 4.4x plus 4,325. So that is our linear equation for this function. So if I want to know how many hours it will take to finish filling the pool, I'm going to need to know how much water, well, I already know how much water it is when it's full. So I'm going to put this 17,300 in for y and solve for x. So that's what that looks like. 17,300 is 4.4x plus the amount of water that was in the pool to start. So if I subtract the 4,325 from both sides, then I get this step, and then dividing by 4.4 gives me 2,949 is approximately x. Okay, so that seems like a lot of time, but if I come back here and check, I realize, oh, that's minutes. My rate here is 4.4 gallons per minute. So this is the number of minutes. So since I'm asked how many hours it's going to take to fill the pool, I need to do some converting. So to convert minutes to hours, I'm going to divide by 60, and notice that it's about 49 hours that it's going to take to fill the pool, a little bit over 49. Okay, for this last example, we're not really given a context of what these numbers are. It's a function with an input and an output, and we're asked to find the equation that describes the function, and then complete the table using the rule. Okay, so we have these inputs and outputs. We know that this is going to be in the form y equals mx plus b. So I just need to know m and b, and I can write this equation. So we know that b is the y-intercept. So if I look over here at my table, the y-intercept is the point on a graph where x is 0. So I've been given the y-intercept. So I know that this equation is going to have a plus 4 because the y-intercept is 4. So now I just need to know the rate. And so I want to look at some of the points that I'm given on the table and see if I can figure out the rate. So the rate is the slope, it's m. So it's going to be the change in y divided by the change in x. And so using these 2 points, 24 minus 4 gives me the change in y, and 4 minus 0 gives me the change in x. That simplifies to 20 over 4, which is 5. So now I know the slope of this line is 5. So I can write this is y is equal to 5x plus the y-intercept, which we already said was 4. So the rule is y equals 5x plus 4. And it would be good to check it with a few points. So let's look here, 10 and 54. So if I put 10 in, 5 times 10 is 50 plus 4 gives me 54. 5 times 11 is 55, plus 4 is 59. So we can see this is this table's consistent. So I'm going to complete the table using my rule, and I'll get 79. 5 times 15, whoops, 5 times 15 is 75, and plus 4 is 79. Then I get 104 and 119 using the same method. Okay, so in this lesson we have seen that that we can, for a linear equation in the form of y equals mx plus b, can describe a rule for a function, and that any function that can be defined with a linear equation, we'll call it a linear function. So that kind of, it makes a lot of sense. Problems involving constant rate of change or a proportional relationship can be described by linear functions. So just as a kind of a recap on proportional relationships and constant rate of change, remember, if you're going to have a proportional relationship, then it's going to need to go through the origin. Those are those where they can be written y equals mx. That's what we call a proportional relationship. And those are lines, but linear equations don't necessarily have to go through the origin, and these would have what be y equals mx plus b plus the y-intercept. So there's a difference between a proportional relationship going through the origin and just a linear relationship in general. All right, good luck with the problem set on that. We'll see you back here for lesson 4.